Hello, I'm Mehrdad Mirzai from SUNY Albany. Today I will be presenting our paper, which is a joint work with Dr. Sahibi from University of Albany and Dr. Brasilovsky from University of Pittsburgh. In this paper, we propose a model to detect efficient versus inefficient learning behaviors in students using their behavior pattern structures. Previous researchers have shown that student learning patterns extracted from their problem-solving sequences represent studying traits. These patterns are consistent and stable in students, as experimented in different sections of the semester and for different difficulty levels in learning materials. These studies demonstrated that only a few performance-related factors can be observed in studying patterns. Here the question is, can we detect performance-related patterns from trait-related patterns? This is a difficult task because there isn't a direct relation between the patterns and students' performance. In this work, we would like to answer this question, considering that there are underlying similarities and differences between the students' sequential patterns. We build our model based on some assumptions. The assumptions are there are common patterns among all students. There are specific patterns for low and high performance students. Common patterns are similar to each other and specific patterns are similar to each other too. So we need to find student micropatterns, specify low versus high performance students, and tease out the common and distinct patterns between students that considers pattern similarities. I will walk through these steps in my today's presentation. Before going through the methodology, first I introduce the dataset and the system used in this work. The dataset includes students' interactions with two types of learning materials from a Java programming course. These learning materials are programming problems and examples. In the programming problems, the students are shown a piece of code and are required to answer questions about the output of the code. The examples are small pieces of code with explanations for some line of code. Each problem and example are labeled with a course topic. Although the course is organized as a sequence of topics, the students are free to choose the topics and learning material that they would like to work on. The dataset also includes the order in which each student accesses the learning materials, the amount of time the students spend, and their success or failure in each attempt on the problems. Also, students take a pre-test and a post-test at the beginning and the end of the course. We consider learning gain, calculated as normalized post-test minus pre-test, that demonstrates the student's performance. This measure shows how much students have learned during the course. First, I show you how we create student micropattern vectors, genomes, or profiles. We got this idea from Guerra et al. To model students' learning behaviors and to profile their interaction sequences as behavior vectors. So we start labeling the actions and construct sequences from these labeled actions. The key idea of this approach is to build the compact characteristics of student problem solving and example reading behavior on the level of micropatterns. To build a pattern vector from extracted micropatterns, we start by finding proper micropatterns and then build a pattern vector for students such that the vector represents the frequencies of different micropatterns occurrences in the student interaction logs. Here I explain the details of constructing activity sequences from students' behavior. So, what do we mean by behavior? Our focus is to represent student sequences in a way that can capture the repetitive action on different learning material types. We focus on 4 interaction characteristics: the learning materials topic that the student is working on, the amount of time the student spends on a learning material, the type of that learning material, either it is an example or a problem, and the success or failure of student in solving problems. So, we label students' example reading interactions with the letter E, and for problems, we show the successful attempts by S and the failed ones by F. If the activity duration is less than a specific threshold, we use a lowercase letter, and if it is greater than the threshold, we use a capital letter to represent it. The used threshold is the median time that all students have spent on that problem or example. Next, We use these topics to separate student activity sequences into smaller sessions. This way, each session includes both the problems and examples from the same topic, while the consecutive sessions have different topics. Then, we extract frequent patterns from sequences and build pattern frequency vectors to represent the behavior in a way that is ready for further analysis. So, how can we do this? To detect these micropatterns, we select the ones that are significantly repeated in all student sequences while being long enough to be meaningful. We use the CM-span, which is a frequent pattern mining algorithm, to extract high support patterns from the sequences. In total, we find 77 micropatterns and we use them as features. The top 10 most frequent micropatterns are shown in this table. To build student activity feature vectors, we count the number of times each micropattern is observed in student sequences as the feature value for that micropattern. To eliminate the sequence length effect, we normalize each student's feature vector such that the feature values in each vector sums to 1. Eventually, given 77 micropatterns, we represent each student as a normalized vector. After creating the student pattern vectors, we create the high and low performing student pattern matrices. This workflow demonstrates the process of extracting patterns from sequences. After building pattern vectors, we build a student pattern matrix. Then we separate student pattern matrices according to their performances, which is normalized learning gain in this case. We divide the students into two groups based on their normalized learning gain, such that the top 40% of students are categorized as high-performance students, and the bottom 40% of the students are categorized as low-performance students. We omit the middle 20% of the students to have a clear distinction between the low and high-performance groups while keeping enough data points to maintain an acceptable level of significance. Now, we are ready to find the performance-related and trait-based patterns in students. To do this, we propose a discriminative model to detect 3 sets of micropatterns: a set containing common patterns among the student groups, a set containing patterns specific for high-performance students, and a set containing patterns specific for low-performance students. Having 2 sets of patterns for low-performance students and high-performance students, we want to find patterns from each set, such that the set of patterns are common between the 2 groups of students and 2 sets that are specific for them. We can obtain the non-negative matrix approximation for each input matrix with minimizing this equation. To find common and distinct patterns, we expect to see some similar trait latent factors and some distinct performance latent factors in matrices x1 and x2. Therefore, we divide pattern latent factor matrices W1 and W2 to have a set of common latent factors and a set of distinct latent factors that are shown here. Similarly, we define common trait-based and performance-based latent factors for students. To make sure that the common parts are similar in both student groups, we add the third constraint, which is a Frobenius norm, in the formula below. Also, to make sure that the distinct parts are far from each other in 2 different student groups, we add the fourth term, which is a proportion with a cosine similarity between distinct pattern latent factors. But so far we haven't used an important source of information, that some patterns are more similar to each other compared to other patterns. So we expect the patterns in each group of trait-based or performance-based to be similar to each other. To use this information, we introduce a similarity measure between micropatterns and update our objective function accordingly. As we saw, the extracted micropatterns are mini-sequences of student activities which have structural motifs that are important in our application. Here we propose a new measure to calculate the structural similarity between patterns. So we first build a distance measure based on the Levenshtein distance between 2 patterns. The Levenshtein distance counts the minimum number of insertions, deletions, or substitutions that are required to change the string sequence into another one. For example, for 2 strings capital F SS and capital S SS, we can see that the Levenshtein distance between them and SSS is 1. But in our application, since in capital SSS, the student continues to succeed in 3 consecutive attempts, it should be more similar to SSS as compared to capital FSS. As a result, we modify the Levenshtein distance to adapt it to our application. We weight the edits such that attempts of the same type or length are assumed to be more similar and have less distance between them. To define attempt similarities, we create a weight graph as shown in this figure. As a result, we define the substitution edit distance of every 2 labels as the shortest path weight between them. Based on this graph, attempts of the same type, such as capital S and small s, or of the same length, short or long, such as capital S and capital F, have a shorter distance as compared to the ones that have both different types and lengths, such as capital F and small s. Then, we calculate the normalized similarity between 2 patterns, Pi and Pj, and construct a matrix that has the similarity between each 2 patterns. Having the structural similarities between the micropatterns in a similarity matrix S, we augment our factorization model to impose these similarities. We use the assumption that structural pattern similarities that are discovered by our proposed distance function should be equivalent to pattern similarities that we discover using the factorization of student vectors. So, we concatenate the pattern latent factor matrices W1 and W2 from the decomposition of X1 and X2 to construct a pattern latent matrix that includes both common and distinct pattern latent factors from both high and low performing students. Then, we calculate the similarity matrix WW transpose as the latent factor based similarity between these patterns. We expect that this latent factor-based similarity matrix resembles the structural similarity between patterns. Here, epsilon is a parameter that the model learns to control for the potential scaling effects. Eventually, this is our full factorization model. We add pattern similarities as an additional Frobenius norm constraint to the objective function. To learn the model parameters and find the matrices, we use the alternative gradient descent optimization algorithm. This model satisfies the assumptions that we mentioned earlier. To analyze the patterns, we build a matrix from the decomposed matrices that contains all the patterns. The model imposes common latent factors to be similar, so we take the average of them. Next, we concatenate the average matrix with low and high performance latent factors to construct a pattern latent factor matrix as the last step shown in this figure. In this matrix, the columns on the left represent the common latent factors, the columns in the middle are discriminative latent factors for low performance students, and the last columns on the right side are the latent factors of high performance students. The matrix has the patterns and the latent factors, but how can we find which patterns are common between low performance students and which patterns are specific for them? So, we analyze the discovered pattern latent factors by clustering them into different groups. By performing clustering on this pattern latent matrix, we find distinct clusters among them. The experiments show that spectral clustering with 6 clusters have a better distinction among patterns. This heat map illustrates the matrix arranged into the discovered clusters. The color intensity shows the strength of a pattern cluster in each set of latent factors. The rows represent micropatterns and the columns are latent factors. The clusters of the patterns are separated with horizontal lines and sets of common versus distinct latent factors are separated with vertical lines. As we can see, the patterns in each cluster have meaningful similarities. For example, the patterns that end with a short successful attempt in solving a problem, such as SSS, capital FS, capital SS, and SSSS are in one cluster. The patterns containing short example readings, EE and EEE, are in one cluster, and the patterns that start with long attempts are in another cluster, capital SS, capital F, capital S, capital F, capital F, and capital S, S, S. This shows the effectiveness of the imposed structural similarity measure. By looking at different common and distinct latent factors in the heat map, we see meaningful patterns among them. For example, the third pattern cluster with multiple short successes in a row has a higher weight in distinct low performance latent factors and a low weight in high performance and common factors. This means that the students who persist in solving the problems of the same topic quickly without spending enough time on them tend to realize lower gain. Next, we analyze the discovered student latent matrices to see what the latent factors show us about student behaviors within the low-performing and high-performing group of students. We look at the different latent patterns in high and low learning gain students to see if there are any indicators of the other performance measures in them. So, we calculate the Spearman correlation between the latent factors in these two matrices and the students' pre-test and post-test scores. The significant results are shown in this table. We can see that for low learning gain latent factors, latent factor number 3 has a slight but significant negative correlation with students' post-test score. This means that low learning gain students who have a high post-test score show less of this latent behavior compared to the ones that have a low post-test score. As we can see in high performance latent factors, latent factor number 4 has a small but significant positive correlation with students' pre-test scores. It means that high learning gain students who have a high pre-test scores show more of this latent behavior as compared to the ones that have a low pre-test score. Now let's look at the heat map to see what we can conclude. On the right side, we can see a part of the heat map from clustering matrix. For low learning gain students, the latent factor number 3 corresponds to latent factor number 16 in this matrix. We can clearly see that patterns with multiple short successes all belong to this latent factor. This observation confirms the ineffectiveness of repetitive short success attempts. The students who do not gain much knowledge during the class and have a low performance at the end of it are the ones who aimlessly repeat the same topic well after mastering it and avoid moving on to the other topics. Latent factor number 4, which corresponds to latent factor 26 in high performance latent factors, has a small but significant positive correlation with students' pre-test scores. This latent factor has the least association with example reading activities which are in cluster 4, while being more prevalent in the other pattern clusters. Interestingly, it shows that high learning gain students who already have a high prior level of knowledge when starting the course, indicated by a high pretest, do not read the examples that are provided in the learning systems. On the other hand, reading examples while having a low prior level of knowledge is associated with students that have high learning gains. In this paper, we propose the framework to discriminate learning behavior trait patterns versus performance indicator patterns from student sequences in an online learning environment. We discovered meaningful patterns clusters based on the latent factors that we find using discriminative non-negative matrix factorization. Based on these discoveries, we could find efficient and inefficient learning patterns from students' behavior. You can try our code, which is available online at this address on the GitHub. Thank you so much for attending my presentation.